Our next talk is going to be on the topic of when to commit to an action in online planning, and it's going to be given by Tianyi. I apologize if I've mispronounced that.
It's correct. Perfect.
Great to hear.
Yeah.
Take it away. Thank you.
Okay. So hello everyone. My name is Tianyi. This is joint work with the Wheeler, Shahaf, Eyal, and Erez. And in this presentation, I'm going to talk about when to commit to an action in online planning. So just some background information. We are dealing with classical planning environments, meaning we want to plan for a single agent, and then we assume discrete state, discrete action, and then we assume complete observability, and then we assume we have deterministic state transition. And more importantly, we want to deal with online planning, meaning we want to interleaving planning and execution. All right, so here's an example of highway navigation. Everybody has this experience that if we plan for too long in a highway, we can easily miss the right exit, right? So in these scenarios, we do want to perform planning under some time pressure. So we don't want to plan for too long. Maybe we don't have time to, if we do search, we don't have time to search all the way to the goal. Right. So one way to deal with this is in search is called a real-time heuristic search to do online planning. So the way it does is the agent only performs search for a bounded time. So we do some search, and then we have this search frontiers or the fringe nodes, the frontier nodes, and then we can find the best frontier node. And then we can commit to a top level action that can leading the agent move towards to the best frontier node, right? So then when we commit this action, agent can executing this action, and then in parallel, we can reroute the search tree, maybe from this red node, and then doing another round of search, and then find the next best frontier node, and then commit to the best top level action. And then in this online planning, what it does, it's interleaving this search and the action execution until the agent reach a goal. All right, this is also called a receding horizon control. So the problem we want to study here is a meta level problem. We want to decide whether we want to commit or not commit each action in the best prefix path. So here's already some fixed strategy proposed. For example, the one I just talked about is called always commit one, which is proposed in the original RTA star paper by Richard Koff. So you have this best prefix, right, of best path, and then every time you only commit one action, and then you let the agent moving, and then you reroute the search tree from here and then search. And then also there's another tree in the spectrum is always commit all. You always commit all the way to the search frontier, which is proposed in the original Erez SRT star paper by Sven Koenig and his student Sun Xiaoxun, and also proposed used in Alison and Wheeler's dynamic F-hat paper. So here's what we have right now. So in this work, we want to study, instead of in this too extreme in the spectrum, right? Can we do better? So why we don't necessarily want to do this extreme? For example, in this search tree example here, if we commit all and all the way to the frontier, it can be too risky, right? Because we are doing, we haven't searched all the way to the goal yet. So we are in this bounded rationality settings, right? We do have value uncertainties in our frontier nodes, right? Although it has some heuristics, looks like it's the best right now, but not necessarily, right? Maybe the second best, the blue node here could actually be the best action, best, thing we want to do in the future. So there's some uncertainty happens in the frontiers. So we do not want to commit all the way to the frontier. So on the other hand, if we always commit one, it can be too conservative, right? So ideally we want to commit if an action in the prefix is certainly the best. so that we can gain more planning time for the next iteration. For example, in this scenario, maybe we want to commit 3 actions. So because we know that moving up is actually certainly the not good thing to do, right? So but after that we are not sure, so we want to reroute the search tree up here for the next iteration, and then so that we can gain 3 action duration time for the next search iteration. So we want to find a principled way to do this, to find a commitment strategy. It's a meta level problem, all right? So we in this work we propose this flexible action commitment search. So we have to make some assumptions before we dive into how it works. About the system. So we assume the system cannot be uncontrolled. So we would be forced to commit if the action queue is empty. So as you can see here in this tree, we have some committed action. We call it a committed queue, which is all these red nodes here, right? This queue cannot be empty. So if we already finished the last action in the queue, we have to force to commit to the best top level we have. And then we assume we have this search tree structure, meaning order of decision is fixed. And then we again we assume deterministic system. We don't need to replan. So and then we only deal with the commitment strategy after the search finishes, right? So it will perform the look ahead search, and then once search is done, we want to decide how many actions we want to commit. Here's the idea. So we want to propose this principled way to make this meta level decision, all right? So say we have this committed queue, and then we are now executing this current action C leading towards to state S, right? So, and then on the right-hand side is the timeline we have. We are at this now here. Before we reach S. So when we reach S, when S finishes, we must decide either goes to alpha or beta, right? So we have this dr remaining duration for S, right? And then we have this df. It's a full duration for action. So we assume uniform action duration. So then in this situation, and then we have this search tree, search already finishes, and then we know alpha is the best top level action under each node. So alpha would be the best child for alpha. So alpha is always better than beta, all right? So we already know that. We just have some uncertainties inside. So then what we can do is we either commit or not commit to the best top level, which is alpha, right? So we want to evaluate the difference of them. So what we do is, and what happens if we commit, right? If we commit, what we can do is we can using all the remaining time plus the full duration to reasoning below the subtree and the alpha. So this green box here. If we commit, we can using all the time to reason in the alpha. Right. If we don't commit, on the other hand, we have to keep reasoning under the current subtree, which is S here, right? So we have to using the remaining time to reason under S, and then when S finishes, we have to reason under either alpha or beta, depending on what's the action we commit to by the time. So basically the difference is, we commit, we can allocate all the search time to alpha subtree. Otherwise, we have to keep reasoning under S. So then once we have this difference, we want to calculate the utility, right? So here's how we want to compute the effect of either doing more search or less search under each node. So we want to estimate the belief of where f hat will be after search. F hat is the expected value under each top level node, frontier node, all right? And so it's a sort of expected cost, total cost, right? So we approximate that distribution as a Gaussian distribution, which the mean is sitting at the current expected value we have. And then we have a variance, which is a function of the distance to go of this frontier node, and then also the duration it can use to do reasoning under this node. So by plugging different search time, we can reason about have a different distribution of the expected utility under the leaf node. So then once we have that, we can compute the utility of either commit or not commit, right? So if we commit, what we do is we compute the expected minimum given the two distribution under alpha alpha and alpha beta. And then plug in D, where D is the full time, D reminder duration plus for duration divided by 2, because we assume uniform distributed the search time under all the leaves, among all the leaves. And then if we don't commit, we can do the same, but we would compute the possibility of after DR, it will choose alpha or beta, and then using that as a weighted utility of under alpha and beta. But very similar calculations, please see for details in our paper. But once we have these two utility, we can easily decide if we commit only when the utility of commit is larger than the utility of not commit, right? So once we decide to commit alpha, we do the same reasoning for alpha alpha, all the way to the frontier, and so that we can decide how many actions we want to commit to. All right, so this is the idea. We testing this idea in a syntactic grid pathfinding domain, where we put some tar pits on the left. The red tar pits would have high cost if your agent step into these tar pits. So we want to find a path from initial start to the goal, and while executing, right? This is online settings. So do some search and then commit an action, do some search and then commit an action. So the tar pit area would harm for the reckless committing. If you always commit all, you're gonna have a high chance to step into these tar pits, and then it will harm your goal achievement time in the end. Well, on the right-hand side, we have this corridor area, which do need a long look ahead to observe. Here's a high, a local minima region, high cost region here, because the entrance of the door is here and then the goal is lower. So the Euclidean distance heuristic would drag the search towards down there. So if you don't have a large enough look ahead, you wouldn't observe there's a high cost, local minima here. And then in the middle, we have this empty area, which would help us gain more look ahead. All right, there's no harm to commit in this empty area. So we test it, so as expected, and when we run map with only the left tar pit area, and the commit all strategies, the fixed strategies, commit all perform badly, right? Even with dynamic F hat, we have a sort of factor of 4, way better than that. So the y-axis is a goal achievement time as a factor of optimal. So the optimal is a like an oracle, a planner, which it doesn't have to plan. It will right away executing the optimal A* plan. And then if we test it on the only corridor area on the right, it can all the algorithm have a really small action cube form badly. And then when we combine them, our algorithm, our flexible strategy actually still performs the best, consistently performs the best. So the x-axis is the the look ahead limits, right? The time bound we have. We do all the experiments in terms of node expansions. So yeah, to summarize, facts, it starts to explore a principled way of doing online action commitment. And then we see it actually can perform better than fixed strategies in this syntactic domain. And then the takeaway message would be, if we do deliberation on how to allocate search effort, it can actually benefit online planning, right? And then more broadly, meta reasoning really pays off when we have to plan under time pressure. With that, I'm gonna stop here and welcome any questions. Thank you.
Thank you very much, Tianyi. It was very interesting. Can I invite any questions from the audience? Okay, anything in chat? Nope. Okay, so I'll ask a question. So have you ever encountered any cycles in your tree search? Because that would obviously put a wrench in your plan.
Yes, yes, absolutely a good point. So in this scenario, we do have a a cycle detection in our planning. So it's just like you have some closed list, so you can prune away all the states you have visited before, right? So we do assume we can prune away the cycles we have, but it's a really good point in terms of we have made this assumption that we don't need to uncommit action, right? So that's a very interesting scenario, that if we are allowed to uncommit action, maybe we would step into some previous state before and then reasoning from there. But we haven't do more sophisticated reasoning on that part yet.
Thank you. Can anybody else think of an interesting question to ask Tianyi? Okay. Thank you very much for your talk. Let's thank the speaker. And if Sriram, if you're giving a presentation, if you could share your screen in preparation for the next talk on analyzing the efficacy of flexible execution, replanning, and plan optimization for a planetary lander. Daniel, are you here?
Hi, so this is Joe Russino. I'm going to be presenting this on Daniel's behalf today.
Oh,
can you guys hear me?
Yep, I can.
No worries.
It's fine. Thank you. Yep. So whenever you're ready, go ahead.
Okay. Yeah, thanks. So my name is Joe. I'm going to be presenting this work on using flexible execution, replanning, and model parameter updates to address environmental uncertainty for a planetary lander. And yeah, I just want to mention that this work was led by Daniel Wang. Unfortunately, he's unable to participate in this session today, but I want to acknowledge him both for doing the bulk of this work and also providing the slide deck for us.
I'm sorry, can I just interrupt a second?
Yes.
Could you perhaps make the main slide full screen, because we're seeing.
Are we not full screen? I'm sorry.
Quite small.
Let's see what I can do here.
So Joe, we're seeing the presenter view.
Okay. So let's fix this. Share screen. You should be seeing now just the slides. Is that right?
This is good. Thank you.
Yes. Okay. All right. So a little bit of background. This work was done in the context of the Europa lander mission concept. So the objective of this mission concept is to excavate the surface of Europa, the moon of Jupiter, collect and analyze material samples for potential biosignatures, and then communicate that data back to Earth. With some secondary objectives, including collecting seismographic data and panoramic imagery of the surface. This presents a set of challenges that we haven't really faced before on previous missions. In particular, there's a finite non-rechargeable battery supply. We also have large communication blackouts with the Earth, so we can only communicate 42 out of every 84 hours, and just unprecedented levels of model uncertainty. So these things motivate significant levels of autonomy, because the lander has a limited lifetime, can't afford to wait for ground instructions necessarily, and there's not a lot there's less knowledge than we would like of the surface of Europa, so that limits the quality of the a priori estimates of that we make about the tasks that we want to execute. For example, how much time or energy it might take to perform some of these robotic activities, like excavating the surface, collecting samples, and those sorts of things. And so this means that the system is going to have to react to off-nominal conditions and just plan using sort of the best up-to-date knowledge of the surface that we have. So as I said, these challenges motivate a higher level of autonomy, and we're focusing on the integrated planning and execution part of that here today. In particular, we want to use knowledge that we've gained at execution time to drive our planning. We're going to be talking a little bit about flexible execution of tasks and also about replanning with plan optimization. And the work that we're presenting here today mostly centers around creating a model to predict the impact of using those techniques on the quality of the missions that we perform. So this is an illustration of a basic surface mission that we might perform on the surface of Europa. So this kind of represents the mission at a very high level, and this is a very focused mission. So there's sort of two things that we're doing. One is we've got these ongoing panorama and seismography tasks, and then we've got this set of sampling tasks. And in the sampling tasks, what we're doing is we're looking for the presence of biosignatures on the surface of Europa. And so what we expect to need to do is to excavate off a layer of material that we suspect will have been sterilized by the radiation environment. And then within that excavated area, collect one or more samples of the material underneath, transfer those samples into a compartment on board the lander containing a set of instruments, and then process and analyze those samples and communicate the data generated by those analyses back to Earth. We model this problem using hierarchical task network to compile the domain-specific knowledge of the dependency structure into the task network. In an HTN, the hierarchical tasks are decomposed into a set of subtasks, and we high level parent tasks and further in those tasks. So parent tasks might decompose into different tasks, and we'll read each of these sets as potential decompositions in that parent task. And then finally, we refer to tasks with no decompositions as primitive tasks. So the primitive tasks represent things that the lander can be directly commanded to perform. Decompositions provide a number of benefits in our planning approach, significantly reducing the planned search space. And then in addition, we can treat all of the subtasks of a parent task as a singular block for planning purposes. The lander, and this is an important concept, the lander only achieves utility after completing an entire sequence of sample, analyze, and communicate. The ultimate goal for a Europa lander would be to analyze the surface material and communicate the resulting data products back to Earth. And so to reward accomplishing these goals, we assign utility to tasks such as excavation and sample collection and seismographic data collection. But crucially, we do not award any utility until the lander communicates the data down to Earth. In the HTN framework, this means the tasks in a hierarchy produce utility only if the full decomposition is executed. And it's important to note that that utility is only achieved when the data is downlinked back to Earth. That's true for both sampling tasks and seismographic and panorama tasks. So this is the planning and execution framework that we're working with on this project is based on MXEC, which is an integrated planning and execution system that was originally designed for the Europa Clipper mission. There are two main features of this that we want to focus on today. The first is flexible execution, and the second is replanning with plan optimization. So flexible execution, in our case, what we're talking about is allowing for marginal plan changes without failing outright. So for example, we might change the tasks, the start time of a particular task due to delays in other work that generated pre-constraints. And in the replanning case, we're replanning, so we update the system's plan at execution time using up-to-date state knowledge. So for example, we might measure things about the surface like surface hardness, or observe things about our tasks like how long certain robotics tasks take, and incorporate that when we replan. Here's an overview of the planning algorithm that we're using. So first, a pre-processing step flattens the task decompositions into a single layer, such that parent tasks decompose into a chain consisting only of primitive, non-hierarchical subtasks. And this allows us to assign utility and energy costs directly to each composition because its breakdown into disparate subtasks has already been performed. And then each decomposition's utility is the sum of each of its subtasks' utility. And the same is true for the tasks. This step is performed once at the start for domain model. So it's an offline step. And then our planning algorithm uses the HTN model of the Europa lander mission to build a search graph with nodes holding partial plans and edges holding task decompositions. And we perform a heuristic guided branch and bound search on this graph and select the best plan that we've explored. The algorithm consists of 4 phases. There's a pre-processing, initialization, and then the exploration step, which is described here on the slide, and then the final plan selection. So the heuristic we described here, it's a product of the utility of the partial plan contained in the node that we're starting with, and then the utility of the task that we're proposing adding to that plan divided by its energy cost. So we're interested in the energy cost in particular because this mission, one of the sort of interesting features of this mission is that we've got a finite non-renewable battery. So every bit of energy that we use really counts. And so with this heuristic, we're favoring tasks that earn us a high amount of utility per unit energy. So then we've got a final selection phase where our search is bounded by total energy costs, and then we've got an additional bound on the number of candidates that we explore. And then on termination, we just choose the plan we've generated that has the highest utility. We want our planning system to respond intelligently to stochasticity at execution time, since we expect this to be a significant factor in our domain. So planning and execution are integrated, and in order to respond to variation and therefore better optimize the overall utility achieved. So we use 2 different techniques primarily. It's flexible execution and replanning with plan optimization. Flexible execution is, in our case, it's a lightweight rescheduling algorithm that runs at a much higher cadence than the planner. So the algorithm has 2 main properties. First, it's significantly less costly than replanning. It's also significantly less powerful than replanning, but despite its limited scope, it's valuable because we can run it frequently. It allows the system to handle less severe unexpected events without incurring the cost of replanning. So in our system, this consists of 2 main components. The first is task push. So if a task's preconditions are not met, then before failing the task, we allow it to wait for some amount of time for inconsistencies to resolve. So a situation like this might occur, for example, if previous dependencies are unexpectedly delayed. We will push the start time of task forward in the plan. And this is implemented as a callback that's run before task is dispatched to the execution system. The executive tests the task's preconditions and delays dispatch until either the conditions have been met or until the task's waiting timeout has been exceeded. The second component of flexible execution is automated retrying. So after a task completes with failure, flexible execution can immediately reschedule the task if its preconditions are still met. The plan is then updated to account for the new predicted end time of the task, as well as additional resource usage. And here the system short circuits a simple failure response, avoiding planning costs for failures wherever possible. So in the context of the Europa lander domain, flexible execution offers significant value despite its simplicity, because significant noise is expected in resource impact. Providing a low-cost method for handling mismatches in resource use predictions often avoids the cost associated with either replanning or a more costly step like waiting for a ground input. So for example, if we're heating a joint on the lander, which is a precondition for movement, and that heating occurs more slowly than predicted, we might handle that by re-triggering the heating operation or by delaying the R movement, either of which would be significant to resolve that issue. And then for more complex failure responses, simply retrying tasks or delaying them might be insufficient. So in these cases, we turn to online replanning. So this allows us to make use of online state updates. So we can respond to variation in the original plan predictions. In our framework, we measure the value of each resource being modeled. And then when replanning, the planner uses the actual measured value of that state rather than our prior. And this allows us to update our predicted impacts according to what's realistic depending on what we've observed. When tasks fail, their state impacts are usually not realized, and so replanning provides a mechanism to respond to these problems in a more complex manner than just retrying a task. In addition, this allows us to make use of adjustments to predicted utility for tasks. So for example, we might discover that the task, let's say, consumes more or less energy than expected. We also might discover that certain tasks produce more value than we predicted. So for example, in the Europa Lander domain, we might discover a biosignature at a particular location when sampling, and then we can use that to update our utility predictions on tasks sample from around where that sample was collected. This is our modeling frame, and this is kind of the core of this work. So in this framework, we examined 4 planning execution strategies, which we call the static strategy, the strategy, flexible execution, and replanning. Excuse me. So using the static strategy, a plan is generated before execution time and then executed without any changes, and no responses are made. So any task failure results in termination of plan execution. In the ground strategy, we introduce a mechanism for failure resolution that involves waiting for ground input. So we communicate with the ground, wait for a relatively long period of time for ground to respond with an update to resolve whatever issue it experienced. And I should note that that comes at a cost, because there's a hotel load and we've got a finite battery that can't be replenished. So we're spending energy waiting for the ground. We assume that ground input is able to resolve all failures. But our plan is still pre-generated like in the static case, but task failures can be handled without termination of execution. And in the flexible execution strategy, we allow for flexible execution, which is, as I said, less costly, but we model this as only being able to handle a fraction of possible failures, with other failures handled by the ones that can't be handled by flexible execution, handled by the ground. And then finally, in the replan strategy, we allow for modification of the plan and execution time according to information discovered while running. So this provides another failure resolution mechanism that we assume is more powerful than flexible execution, but less powerful than waiting for the ground. And in addition, also allows for the optimization of plans according to newly discovered utility. So this sort of the replanning serves 2 purposes. We can resolve task failures, and we can change the plan to increase our overall utility gain. All right, so in this context, we predict that the overall utility achievement of a plan using an estimate of average utility per unit cost, which is a use of average here. Then assuming that the tasks always succeed, our expected utility for a plan would be our total battery capacity times that average utility per unit energy. To factor in task failure, we assume that tasks fail with some probability, P of failure, and then we assume that task failures follow Poisson distribution in this case. The first planning and execution strategy that we're looking at here is the static strategy. And since in this strategy, we just terminate on our first failure, the overall expected utility achieved is based on how long we can expect to execute before encountering our first failure, which is basically the probability of failure of any one task. Excuse me. In the ground strategy, going to ground to seek manual intervention. So to model this in our framework, we assume that waiting for ground there's a cost of W and plan execution. So this will improve on our expected utility from the static plan with this second term, which represents how much utility we're foregoing while we spend energy waiting for the ground to resolve a failure and not doing productive work in the meantime. In the flexible execution strategy, we introduce flexible execution and assume that some subset of task failures can be resolved with that feature. So we denote the probability of a task failing in that way as P of FE, and then note that the probability of a task failing in a way that's resolvable by flexible execution is a subset of all failures. We assume that flexible execution has a negligible cost, and so this here describes the utility that we expect to achieve for a plan using this strategy. It has the same structure as the model associated with ground intervention only strategy, but we gain back some additional utility for issues that can be resolved using flexible execution at an associated lower cost. And then finally, we consider the replan strategy, which incorporates flexible execution and replanning with plan optimization. Unlike flexible execution, replanning incurs some non-negligible costs, C sub R. We assume that, like flexible execution, replanning is able to resolve some subset of task failures, in this case, a larger subset than a flexible execution. And as previously mentioned, replanning improves overall utility achievement through two mechanisms. The first is the failure recovery, and the second is plan optimization given execution time knowledge. So to model the plan optimization part, we provide our planning system with opportunities to discover utility at certain points during execution. And then we denote the number of such opportunities as D and the expected additional utility discovered as U sub D here. And so real quick, I just had some results of an empirical evaluation that was done. So the setup here is that we obtain the average utility using a simulation across 50 trials. And then for our model calculation, we use a prescient planner to determine our use of average. We set our failure probability for our tasks at a uniform 0.1. And then we assume that flexible execution is capable of resolving 30% of failures. Replanning is capable of handling an additional 60%. And then I think, as I mentioned before, we assume that ground intervention is able to handle all of the remaining failures. And so briefly, what you can see here compared to the results that would be predicted by the model in green, the blue bars represent the results of our empirical evaluation. In the static strategy, our missions tend to terminate quickly since there are no failure resolution mechanisms. In the ground strategy, this improves our expected utility because we can resolve some of these failures by going to ground, although it costs some energy, and that limits the amount of energy we have to spend doing productive tasks. With the flexible execution strategy, we're able to see a little bit higher utility. And then with our replanning strategy, we see an additional improvement, which we suspect is due both to gaining back some energy with this improved failure resolution and being able to capitalize on the additional utility discovery that we make during execution. And a few things just to note about this, the results generally follow the contour that we expect based on our model. They over or underestimate slightly based on the strategy. We suspect there's a spikiness in the utility of our sort of actual executed missions that's smoothed out in the model by using this average utility per task. Some tasks are worth more than others, and we only actually accrue the utility from those tasks when we successfully downlink the data. And so that may explain some of the discrepancy there. The upper bound on D overestimates the number of utility discovery opportunities. So that's all that I have. Just a few quick conclusions. A mission like the Europa lander mission concept will have limited supervision and a limited finite battery, and this presented some interesting challenges. We presented a model here for analyzing the pros and cons of delegating decisions to the lander itself rather than ground operators. And we suspect in general that as the system gains responsibility, our opportunity for doing performing more efficient missions increases. And we sort of suspect this kind of onboard autonomy to be an enabling technology for future missions like this one, where we've got high degrees of uncertainty and limited opportunities for interaction with ground operators. And that's all I have. Thank you.
Thank you for the great talk. And if I can invite questions from the audience. In the meantime, could I also invite Jack Liu to start sharing his screen and make sure that everything's working correctly for the next talk? Well, do we have any questions for Joseph? Okay, I have one question. So in the pre-processing phase, you organize the subtasks into your hierarchical tasks. You say that based on optimality. During replanning, are those tasks reorganized again based on the updated information that you get from the replanning, from the planning failures and replanning conditions?
No, so that's a good question. Yeah, so we have a fixed task network that includes these alternate decompositions that sort of break down into a sequence of activities, and those remain fixed across the replanning. So those are sort of designed ahead of time by the I guess what you'd say the mission planners, right? To say, okay, well, when we want to collect the sample in a certain manner, there are 2 or 3 different approaches maybe we can take, and they break down into this sequence of tasks, and then those become sort of the options for sampling that, and those form sort of the blocks of tasks that we can schedule, and the planner can choose between them, but the composition of those individual blocks of tasks doesn't change.
Okay, and have you considered or have you tested an approach which is non-hierarchical, just how they would compare in terms of the scientific return or the utility if you just planned with the subtasks alone?
That's a good question. No, we haven't. We sort of started out. We saw in our mission that it seemed like there was a sort of a logical decomposition to the way that some of the group wanted to, I guess, represent the mission, right? So we have this set of sampling loops that we want to perform that have a very similar structure and maybe 1 or a few different ways of performing a sampling activity, and so we saw a natural way to kind of cluster these things and not have to search the full space of our primitive tasks, sort of be able to reduce our search space that way. So we have not tried searching in a kind of non-hierarchical way.
Okay, thank you very much. Thank you again to the speaker. And if there's no more questions, could I invite the next talk? It's going to be on the topic of, do you see what I see? An egocentric view of our pansophical planning problems.
Right, just let me share my screen. Right, can you see it?
Yeah, we can see it just fine.
Okay, all right, cool. I guess I'll start. So my name is Xiaotian. I'm a master's student at Queen's University in Kingston, Canada. I'll be presenting our paper called Do You See What I See? An Egocentric View of Our Pansophical Planning Problems. The paper is done by me, my co-author Alison Paredes, and my supervisor Christian Muse. So our motivation is that classical planning are pansophical, where all the objects and relationships are known in advance and are always observable. However, many planning problems are egocentric in nature, where only part of the initial condition can be seen by the agent. Thus, solving an egocentric version of classical planning problem require manual conversion and redefining the problem. This process can be time consuming, and people normally do that according to their own needs, which make it information sharing and generalization across problems and domains a little bit difficult. In this work, we propose a semi-automatic approach for converting classical pansophical planning problem to their egocentric alternatives. There are many existing planning algorithms solves partially observable planning problems, such as conformant, contingent, and epistemic planning. However, these approaches often require belief states, but egocentric agent might not have enough information to properly formulate a belief state. So, for example, new objects or new predicates might not be known in advance. Thus, gradual exploration is often needed for the agent to gather information to properly formulate a plan. For example, in a 2D navigation problem, the agent might not have access to information such as how many location objects there are and what they are. Thus, we believe egocentricity in planning is important and is a parallel paradigm that can complement current partially observable planning methods. In this work, we focus on converting classical planning problems defined in PDDL to egocentric alternatives. We take an object-centric view of the world and assume the world is made of objects and their states and relationships are defined by predicates. We assume that there exists a set of objects that define the egocentric vision of an agent. And then we call these objects anchor objects. We also assume that a planning problem has a set of connection predicate that demonstrate how anchor objects are related to each other. Thus, our algorithms require the user to define a set of anchor objects and connection predicates in any domain. So we use an iterative replanning approach, which extract a subset of the panspherical planning predicates that are observable or seen by the agent. The agent will check whether the original goal can be achieved with the current information, and if not, it will explore to gather more information until the original goal can be reached. We divide our algorithm into two parts. First one is called egocentric subset extractor, which decides which subset of the planning problem is seen by the agents, and then an iterative exploration by replanning algorithm, which facilitate the exploration and information gathering process. We also assume that there's a set of actions. We call them exploration actions. They're the action that agent can take to get to another egocentric state. So together with the anchor object and connection predicates and exploration actions, this will serve as the information the user needs to input for our algorithms. We'll demonstrate our approach with a toy search and rescue example. The goal of this problem is for a robot to search and pick up a person and carry that person to a hospital. The problem has objects such as location, person, robot, etc. And the actions are move the robot, pick up the person, and drop off the person. And the goal is to carry the person to the location of the hospital. So our algorithm first extract the egocentric state from the initial condition. This requires the user to define the anchor object set, which in this case is just the location where the robot currently resides. We then iterate through all the predicate of the original problem. If the predicate contains the 0,0 location in this case, we'll assume that they're observable by the agent. We also include predicates that contains no location objects, such as all the action literals, and assume that they are always observable by the agent. Our algorithm will first check whether the original can be reached, given the current set of the predicate as initial condition. If not, then the other algorithms take over for exploration. So the iterative exploration by replanning algorithm require the user to define the connection predicate types, which in this case is the con predicates, and a set of exploration action, which is the move robot action for this problem. Our algorithm will iterate through the original planning problem and extract all the location objects in the connection predicates that are related to the anchor object defined by the user. Then it will mark these objects as unknown, which indicates give indication of where the robot needs to explore next. The algorithm will then create an exploration action from the move robot action, which are defined by the user, by adding an unknown predicate in the action's precondition and explore that predicate in the effect set. The goal of the original problem will be replaced by exploring one of the unknown anchor objects that are seen by the agent. So once we explore an unknown anchor object, the object will be added to the anchor object set, and a new egocentric problem will be formulated by the algorithm again, and then the process will repeat for replanning until a plan can be found to reach the objective of the original planning problem. So we tested our method in 5 classical planning domains, which we took from PDDL-GEM. And these problems are search and rescue, blocks world, elevators, Sokoban, and Minecraft. And our algorithm worked in 4 of the 5 problems. We found that if the user can define a well-suited set of anchor objects and connection predicates, however, will not work if the user cannot find either of these sets. So for example, if we can clearly define anchor objects and connection predicates, our algorithm works in domain where the notion of an agent is not very obvious at first glance. For example, in the blocks worlds problem, we define the blocks as anchor objects, and these objects are connected by the predicate. Initially, the egocentric view of the world can only observe the blocks A, D, E, F, which are the blocks on top of each stack. The exploration action is defined using the pickup action for information gathering. So with this definition, we can interpret this problem as viewing the blocks from a bird's eye perspective. And then when we lift one of the block, we can see what block is underneath it. And the block world example, as well as the elevator problem, shows that our method works beyond just agent navigation. So our method does not work in the Minecraft domain. Is the reason that we cannot define a anchor, or we cannot define a anchor object set or a connection predicate set. So in this example, the problem is framed in a way where the agent can move to any location in a single step. Thus, the location objects are not connected with each other, and everything is fully observable in the beginning. So this makes connection predicate impossible to define given the planning problem, but it works if we add connection predicate for each of the location and force the agent to move one step at a time. However, this modification needs to be done by the domain designer and shows our method is constrained by how well you define the anchor objects and connection predicates. So in the Sokoban example, it is a similar problem to search and rescue in terms of they are both grid navigation problems. For Sokoban, we added push and block in addition to move as another exploration action. So it works in most instances. However, in one of the problems we tested, our algorithm made a move which resulted in a dead end. Since not all actions in Sokoban are reversible, thus given how much information you're lacking from an egocentric perspective, it's much easier to encounter a dead end compared to a fully observable planning problem. So in conclusion, we believe that egocentricity in planning is important in many applications. And here we proposed a semi-automatic approach to convert classical planning problems to egocentric alternatives. In the future, we would like to test our methods on more complex planning tasks. And then we would like to add dead end detection to detect dead ends given the egocentric information. And finally, I want to see how our algorithm will work in the presence of a belief state and how it can be integrated with some of the partially observable planning approaches, such as conformant and contingent planning. And that is it for my presentation. Any questions?
Thank you very much for the great talk. Can I invite any questions from the audience? Okay. since nobody's speaking up, I can ask a question. So you're saying you want to test in future iterations of the project, you want to test it on more complex domains. Do you have any particular domains in mind from real world examples? So pertaining to the workshop in integrated education?
So
And
I
also,
guess, oh, sorry, go ahead.
And it's two-part question. So if you can answer the first one, I'll ask the next.
We're thinking about scheduling, where the, partial observability and egocentricity is now really well defined, but there are many instances in scheduling that might lead to something like egocentricity. So we want to test that. And also a complex rover planning problem. I think that will be another good way to test this, since rovers need to discover new information and replan accordingly.
Okay, and also sticking with the more complex domains, is there have you guys thought of any way that this could extend to temporal or numeric domains?
We haven't given thoughts to that yet, but yeah. So like one of the things we would like to do is I guess this is unrelated somehow, but the next thing we were planning on doing is to see how belief states works in terms of egocentricity. So how do you properly form belief states when you can only observe like part of the environment and exploration is required? So, but yeah, we haven't thought about any numerical domains.
Okay, thank you. And there's actually a question from Ben Wright. He's asking, can this system take into account partial information? For instance, in that hospital/person example, if someone told the robot the hospital was southwest of its current location, does the system have a way to incorporate that info yet?
So I guess that has to be included in the pansymphorical problem. So our vision for this is that so for an agent, you do know that you need to discover a person, put that person in the hospital. That is the task, but you don't know where the person is, how many locations there are. You need to explore to gather that information. So if we can write that in a partially observable way and with information that are mismatched with reality, how do we use an egocentric way to solve that problem with the right planning formulation but the wrong information? So any extra things need to be added should be added to the fully observable version of this problem, and then to solve that from there. I don't know if that answers the question.
I just add there's one extra element on that. If you recall, Jack, we stopped just short of being smart about where we explore, right? And
right.
And part of the future work is like explore to avoid dead ends if you can type of deal. So your final explore action should be something reversible. But if you can turn high level advice at southwest into explore this boundary of what you see a little bit better, then you can target your exploration a little bit better in that way. There's like a rich range of research questions on that. Yeah.
Yep.
Interesting thought. So
thanks.
There's a hand raised, I think.
Yeah, can you hear me?
Yep.
Can you hear me?
Yeah, I can hear you.
Okay, sorry. I was about to ask if you have a way to focus your exploration instead of simply exploring at random, but Christian already referred to that. So I haven't had the chance to lower my hand.
Yeah, I think, exploration, so for all the classic planning problem, we just basically, randomly pick one of the area to explore, but adding, search heuristics and like these type of functions where it can tell us where to explore would definitely be one of the area where we're considering doing more digging into. But yeah, so even with the visual input, how do you with a first person perspective and a planning model on top of it, how do you decide where to explore and how to formulate a symbolic plan from visual inputs? That's one of the area we're also working on right now.
is it related to you're trying to find a plan and you haven't managed to find a plan? Maybe you can focus on the areas that you failed, that seemed promised to the planner but failed
Right.
because of lack of information.
Right. Yeah. So like I guess this will be the more information theory like area of approach. So like how do we gather more information? But this also goes back to like do we need to have a objective function and reward function? How those are like so like things like the plan length, or like do we want to discover more? And we can also play on top of like the goal. We can replace by just finding the person. So like the goal will be like explore more, having more reward in that.